morning. Welcome to Introduction to Photonics. So this week we've been looking at how photons interact with matter, and specifically we've been trying to analyze light generation and amplification. So we'll continue the discussion with a little bit of a practical example. We'll look at the example of why we need amplification, right? So, till the last lecture, we were looking at how amplification, or what are the conditions required to achieve light amplification. Today, we will look at why we need amplification. We'll take the specific example of optical communication, right? So, which is one of the really widespread application of optics in today's world. So we will look at that specific example, and we'll look at why we might need an optical amplifier in that case, and we will try to go ahead and build an optical amplifier today. Okay, so that's what we're going to try to do today. Just to give a quick recap, we started with looking at an elementary system with consisting of two energy levels. We were tracking all the different processes between those two energy levels: absorption, spontaneous emission, stimulated emission. And then we were trying to quantify this emission probability density, which actually it's representing the stimulated emission term. So, you may think of it as the stimulated emission probability density, and or the probability that stimulated emission should happen, and we came up with this expression. And then we were trying to look at specific cases, we're trying to make some specific observations. And one of the first observations we made was, what if we are looking at a source where you have atoms going to the excited state just because of thermal energy, and specifically if the thermal energy is greater than the energy difference between the two atomic energy levels. And in that case, we said we are predominantly getting spontaneous emission. And then there was some discussion about what this graph means. So what we are saying is, for thermal light sources, the probability of finding n photons is something that could be quite broad, right? So which means that it's almost, if you have an average number of photons as 10, if you really go to a very small time scale, right? Let's say a nanosecond time scale. So question is, how small is small? You have a characteristic lifetime for emission, right? In atomic system, we talked about the lifetime being maybe in the order of milliseconds, microseconds, or nanoseconds. For example, the Rhodoman 6G sample that you guys worked with earlier, it has a lifetime in the order of tens of nanoseconds. So if you go to a fraction of that, okay, then you may actually see that even though you have average number as a certain number, the probability that you will find much lower number of photons within that time scale, there is a finite probability for that. There was a discussion at the end of yesterday's lecture as to what this all means. So why do we even then talk about average number being 10 or 20 or whatever, right. Just think of it like this. I was saying that if you go to a really small time scale, you'll find this probability distribution. But what if you try to average over multiple time slots? When if you don't look at nanosecond level, you look at microsecond level or millisecond level, in which case you are averaging the number of photons that you find over that entire time scale. What happens to the distribution? What do you think the distribution would look like? This entire distribution then would essentially collapse to that specific value that we are looking at. Now we say n bar equals to 10, right? The mean number of photons is 10. If you go to a really small time scale, you might find 0 or 1 or 2 or 10 or 20 or 30 even, right? But then if you, that is within this time scale. Now if you average over this much time, you have already seen all these different time slots having these different photons, but when you average them together, you basically say there is a mean number that you get, right. So essentially if you do time averaging, this entire thing is going to collapse to something closer to whatever you are supposed to see, that n bar equal to 10. Okay. So that is what this probability density probability distribution means. So in other words, why are we seeing, I would say that this is a pretty random source, right. This LED is spontaneously emitted source is a pretty random source, but we are seeing a constant intensity from that. Why is that? Because our eye is actually averaging everything over millisecond time scale. Over that millisecond time scale, it is as if n bar equal to 10, right. So that constitutes, if you do time averaging, this constitutes something like this, right, that entire distribution collapses, and that is essentially what we see. We see a time averaged number. Okay. Do you understand this point? Are there any questions about this? Okay. So even a thermal source, even like a incandescent lamp, we don't get to see time slots of nanosecond level. Our eye cannot pick up that. It's integrating over this entire time scale, right. And when you integrate over all the time scale, it actually looks as if it is a constant intensity light source. Okay. So then the next observation we made was optical radiation. If you are emitting optical radiation, then optical radiation has an energy that's much higher than thermal energy, at least at room temperature. So if that's the case, then the probability of emission, probability of stimulated emission is very low. So you're likely to get only spontaneous emission unless you are operating at a point that's well above thermal equilibrium, right. And thermal equilibrium we are defining as if there is only thermal energy given to that medium, right, and so everything is getting to steady state, and we are looking at that. We are actually going by Boltzmann statistics, but we can get out of thermal equilibrium, and that was our observation 3, where we said we can get out of thermal equilibrium if we use this external pumping, right. By using external pumping, we can actually achieve this population inversion, and once you achieve that population inversion, then you could potentially have a large rate of stimulated emission happening compared to spontaneous emission, and through that process we achieve amplification, light amplification, right. That's where we left off things. So, apparent when you look at this picture is the fact that when we look at this atomic system, this lifetime, right, let us say this corresponds to tau 2. What can we say about that lifetime? What do we need ideally for stimulated emission to happen? It should be a very long lifetime, right. So, it is not enough to just get these atoms to go to the higher energy level, but it should stay there until when? Until a photon comes by to stimulate that transition, right. If it is a very short lifetime there, what will happen? It will immediately come down, spontaneously emitting a photon, right, and that is not what we want as far as light amplification is concerned, because the spontaneously emitted photon in this picture corresponds to the same frequency that we want to get, but it is not the same phase as the photon that you want to amplify. Or in other words, the photon that you want to amplify has nothing to do with this emission process, right, if it is a spontaneously emitted photon. So, you do not want, so in other words, when you are trying to amplify these photons, you may have some of these photons going through stimulated emission, which is what we want as far as amplification is concerned, and some photons may be generated, this atom is like tired of sitting there waiting for a photon to come by, nothing is coming by, so I am just going to go down, right. So, it just jumps and then it spontaneously emits a photon, and that photon is not in phase with the photon that is coming in, right. So, that is having some arbitrary phase. So, what happens at the receiver? When you are capturing that photon, you have certain photons that are coming in phase and certain photons that are like arbitrarily coming around, right. So, you can have this constructive destructive interference happening, and that could essentially noise essentially. So, these spontaneously emitted photons as far as an amplification process is concerned would constitute noise, and this is probably a little early to talk about those concepts. We will come back and look at this in much more detail, but I just want to give you a feel for why this is, it is important to have lesser spontaneous emission and more stimulated emission as far as an amplification process is concerned. Okay, but it requires external pumping to create that inversion. It requires a long lifetime for the higher excited energy level. It should be relatively happy staying in that other orbital. It is in no hurry to come down, right. If you have atomic systems where that excited state lifetime is long, that is actually very good. And it so happens that rare earth ions specifically, like erbium, ytterbium, praseodymium, neodymium, terbium, right, all these rare earth ions. Rare earth ions means what? Why do they call it rare earth? you rarely find them in nature, right. So, these rare earth ions actually have relatively long metastable lifetimes, and so most of the light sources that you see other than semiconductor light sources, we will come back and look at that later. Other than semiconductor light sources, most of the other light sources that you see, especially in solid state light sources. So, you can obviously have this amplification happening in all these different states of matter, right, solid, liquid, gas, right. So, what is preferable? Well, if you have a gas, right, so you have to put it into a tube and you have to maintain the purity, so it has to be a vacuum sealed tube, and you need to keep that tube protected from external elements. So, you can say that it is going to be relatively fragile. So, you need to make sure you package it very nicely and all that. So, there is a lot of handling issues with that, and same with liquid state amplifiers. Once again, you could have what you dealt with once again, rhodomin 6G, that is an amplifying medium, right, and that is in the liquid state, but you have to handle that liquid carefully. You had it in a cuvette and you were very careful handling the cuvette, you did not want to like drop it accidentally and spill the liquid and all of that, which would be quite a bit of mess. So, from that perspective, you say solid state lasers. These rare earth ions doped in glass, it's that is actually a highly preferred medium for these amplifiers. So, push for solid state lasers. Traditionally, things have evolved from gas, and so there used to be a lot of gas lasers like argon ion lasers, helium neon laser. We still have a helium neon laser in the lab, you might have seen that, right. That's still around, but that's about the only gas laser that I can think which is around in most of the labs. Most of the other lasers other gas lasers have been taken out or been replaced by solid state lasers. And similarly, there are dye lasers, dye amplifiers, and those have also been, most of them have been replaced by solid state lasers. Okay. So, you need a solid state laser or a solid state amplifier, and you need, in that material, you need a fairly long lifetime. I have been going back and forth with amplifier and laser. Can you imagine how you would build a laser using an amplifier? In general, laser is like an oscillator. Okay, does that give you a clue? How do you take an amplifier and make an oscillator? You might have done this in electronic circuits. Provide feedback, right? So, where do you provide feedback? In this, you put a mirror here, you put a mirror here. So, what is that feedback? It basically feeds back these photons, right, this photons which enhance stimulated emission, because every time they come around, they are going to stimulate these transitions. So, you are going to have stimulated emission, and through that you have a laser. A laser is an acronym for light amplification by stimulated emission of radiation, right. So, this feedback that you provide through a set of mirrors is one configuration, is what can take an amplifier and you can make a laser out of that. Okay, we'll come back to some of those specifics, but let's go on to take an example now. Okay, I will take the example where we need an optical amplifier, right. What is the use of an optical amplifier? Of course, we went ahead and saw the optical amplifier is a basic building block for a laser. So, you may need a laser for multiple applications, but you know we'll defer that discussion, but let's just see where we need an optical amplifier. And it turns out that an optical communication system is one such example where we need an optical amplifier. And what exactly do we need? Well, in an optical communication, you have a transmitter, right, and then you may have a receiver, okay, and the distances between the transmitter and receiver could be the order of hundreds of kilometers, thousands of kilometers, right. We are talking about going across the ocean, Atlantic Ocean, Pacific Ocean. So, right now you know the entire world is wired with optical amplifier, right, with several dozens of strands of optical amplifier, I mean optical fiber, that's what I meant to say, sorry. So, clearly in an, I should have said maybe optical fiber communication system, okay. And clearly when we are using an optical fiber, we go through a long length of optical fiber. That fiber has some inherent attenuation, okay. What causes this attenuation? You know, there may be some scattering happening in the fiber, something called Rayleigh scattering, because the optical fiber is an amorphous, is made of the silica glass, but it's amorphous in nature, and there is a lot of density variations in the glass, okay. And because of those density variations, light tends to get scattered, and that's a process we call as Rayleigh scattering, because the density variations are much smaller to the wavelength of light. And so that works out to be one of the primary causes, and the other cause could be that there are some absorption in the fiber, right, and because of all that you have 0.2 dB per kilometer loss. So, this is the attenuation that you see in a fiber, but at a specific wavelength of 1550 nanometer, right. That is where you get to see this this sort of attenuation, okay. So, you go through this fiber, and let us say you are going through 100 kilometers of this fiber, right. Over 100 kilometers, how much loss would you have? 20 dB, right. So, over 100 kilometers, you are losing 20 dB of the light. So, let us say we have transmitted 1 milliwatt of power from the transmitter. So, you have 20 dB loss, okay, and it is still far away from the receiver, right. So, you need to compensate for that loss. So, what do you need? You need an amplifier, right. So, you need an amplifier with a gain of 20 dB, so that it can boost up the signal again to the original level, and then it can go another 100 kilometers, and there you put another amplifier, and so on, right. So, you can probably can have a series of amplifiers followed by fibers, and you have covered several hundred kilometers with this. Okay. So, this is the typical scenario in an optical fiber communication system, and what we are saying is we need an amplifier which provides a gain of 20 dB. Okay. 20 dB is what? A factor of 20 dB in power, right? It is 10 log is what you take when you do power related measurements. So, 20 dB would correspond to 10 power 2, right. So, that is 100, factor of 100. So, we want to achieve a factor of 100 gain. So, how are we going to do that? But before I do that, you had a question. Sure. So, that is a very good question. The question is, the amplifier, just as we discussed a little while ago, might also have spontaneous emission, and that spontaneous emission could get amplified. That is the problem. Spontaneously emitted photons by themselves are not so much of an issue. They are getting amplified, right. So, they are also multiplying in number along with the signal photons that you want to amplify, and those are all just constituting noise, right. So, this is what we teach at the end of an advanced course on fiber optic communication system, but I'll let out the secret now. So, when you concatenate so many amplifiers, you are accumulating all these spontaneously emitted photons. So, this amplified spontaneous emission, ASC is what we call that, is actually accumulating along that link. So, it is degrading the signal to noise ratio as you go farther and farther. Okay. So, you would think that, hey, I had 1 milliwatt, I came down to 10 microwatt after 100 kilometers, but I put an amplifier, and at the end of the amplifier I got my 1 milliwatt back. So, my signal is back to where it was. So, it is as if it is new. No, that signal also has a fraction of amplified spontaneous emission, and that fraction keeps growing as you go deeper into the link, as you go to and concatenate multiple amplifiers. So, your overall signal to noise ratio keeps reducing, and this is not just optical amplifiers, even other electronic amplifiers. You will see that before you get to do that amplification is the highest signal to noise ratio that you have. You say, okay, but through an amplifier you are amplifying the signal, but you are also amplifying the noise, whatever noise was present at the input, and that amplifier adds its own noise. So, the net effect is the signal to noise ratio is only going to degrade. So, all these amplifiers would have something called noise figure. So, what is noise figure? SNIR at the input divided by SNR at the input divided by SNR at the output. Okay. So, they add their own noise to it. So, you would see that the signal SNR, the signal to noise ratio, is degrading as we go further down that system. Okay. Now that you learned that, you do not have to take that course. I am just joking. No, so let us come back to what we want to do. So, we want to achieve this amplification. Now, how do you build an amplifier? Okay. It turns out that since we are dealing with optical fibers, you do not want to take light out of an optical fiber. You know how difficult it is. Taking light out of an optical fiber, amplifying through some external medium, and then coupling that light back into the fiber, right? You incur losses at all these stages, right? So you would preferably want to have amplification happening within the fiber itself, okay? And guess what? We are lucky because actually there's this professor in University of Southampton, Professor David Payne, who happens to be one of our collaborators also. So he had this invention where you could dope these rare earth ions. Remember I mentioned these rare earth ions are very good, that they have a fairly long lifetime, so they qualify for optical amplification. So he doped a rare earth ion, specifically one ion by named erbium, right? And when you dope erbium into silica, so essentially what we are looking at is, let's just say we are looking at the core of the optical fiber. So you have these erbium ions distributed the core of the optical fiber. We won't go into the details of how erbium got in there. There is some solution doping method and all that. We won't go to the details of that, but if you impregnate this glass with erbium, so the erbium ions are sitting inside, then you could, an erbium specifically has an energy level like this. So you are pumping external energy at 980 nanometers, and it goes to a higher energy level, and erbium is such that it actually comes down to a lower energy level through non-radiative relaxation. And from here, this transition corresponds to 1550, okay. This is actually God given. Specific rare earth ions having, specific energy level structure, right? And so that clearly if you want to get amplification at 1550, the delta E between two energy levels has to be corresponding to 1550, right? So you cannot manufacture an ion to have that particular transition. We're not there yet, okay. So you look for which rare earth ion actually has this transition. To his credit, he found that erbium has this transition at 1550. So he doped erbium into silica. So this is basically a erbium doped silica optical fiber, and then he found that this, if you couple a weak radiation at 1550 nanometer, you can go out with strong radiation or many more number of photons. The photons are counted in terms of their flux density. So the input flux density is very low, but the output flux density is very high. And where did we get that extra energy? Through the pump, right? So we have supplied, somehow we have supplied this 980 nanometer photons also into this medium, okay. And so we got this amplification. So the question is, if we are feeding in 980, according to this picture, you already have 1550 nanometers, right? So why are we feeding in 1550? turn around the question. 1550 is what we want to amplify, right? So, we want to amplify 1550, and to amplify 1550 you need a large number of these erbium ions sitting at that higher energy level, right? To have that many ions at the higher energy level, you need to excite all these erbium ions, and to excite the erbium ions we are feeding in 980, right. So, hope that is clear. So, this is h nu at 1550, and then we are getting this amplification happening through stimulated emission. Okay. So, let us go into some specifics. Let us actually take an elemental system. I do not want to go into the details of erbium yet. Let me just take an elemental system and try to quantify the gain of that system. Okay. So, let us go ahead and try to do that, and to do that I would consider, let us say, a gain medium right, and let us specifically consider a small slice of that. So, the overall length of this gain medium is d, but I am considering a slice between z and z plus dz, okay. And I am also considering certain flux density going into this region, and of course you have a certain flux density coming out, and we want to quantify that now d phi corresponds to the amplification that we have achieved, right. So, this is the picture we want to look at, and of course it corresponds to, let us say, this gain medium is an atomic system. It is a 2-level atomic system with N1 corresponding to the number density in the lower energy level and N2 corresponding to the number density in the higher energy level, and delta E corresponding to the energy difference between the two levels. Okay. So, let us track what all is happening over here. So, what is happening is you have absorption happening, which takes an atom from a lower energy level to a higher energy level. Is it okay that I say from here on just atom? Whenever I am saying an atom is going from lower energy level to a higher energy level, what I mean is an electron is taken from one orbital to another orbital, right. So, let us just say the atom is excited and it is going to that excited higher energy level. So, absorption is happening at a rate that is given by, of course, absorption is going to depend on how many atoms are at that lower energy level. So, N1, and it is going to the excited state with the rate we will call as Wi, okay, where Wi clearly depends on the photon flux density, right, the number of photons that number density of photons that come per unit time, and there is a, like we talked about, all of these are probabilistic events, right. So, it is not like every photon that comes around gets absorbed by an atom. Okay. So, you have a certain probability that a photon will get absorbed by a particular atom, and that probability density we were looking at before, but in the last lecture we said that probability density we will express in terms of sigma, which is known as the transition cross section, right. Sigma is the corresponds to the transition cross section, right, and it is specifically quantifying sigma. I think we did this yesterday, is lambda square over 8 pi multiplied by TSP, which we are calling as the spontaneous lifetime. Now, in general, we say sigma is actually a function of nu. What is nu? Frequency, right. So, what we are implying is that sigma is different for different frequencies. In this case, we have only one transition. So, how many frequencies would it correspond to? It's a very specific frequency that we are talking about, but in reality we would have a bunch of energy levels that are possible in a collection of atoms in material. You will have multiple energy levels that are possible corresponding to the ground state and multiple energies corresponding to the excited state, and there are multiple transitions that are possible between the ground state and the excited state, and each of those transitions have a different possibility, different probability. Okay. So, sigma of mu can be different for different values of frequency, and to account for that we typically use a quantity which we call as g of nu is called the line shape function. Of course, g of nu equals to 1 for this particular case, because we are just looking at just unitary transition, but g of nu can take, it can be normalized to 1 and can take different fractional values for different frequencies in general. We will come back look at some specific examples on that later on, but key thing is there is some transition cross section which determines this rate at which absorption takes place. And similarly, you can say that stimulated emission will also happen at a rate that will be given by, that will depend on number of atoms at that excited state. So, N2 times Wi, right. Is Wi going to be different for absorption versus emission? If we are considering one single transition, right, a single pair of energy levels, that is not going to be different. So, this is the same Wi that you have for absorption, the same Wi you have for emission also. Okay. And we will assume that spontaneous emission is negligible in this case. Okay. We will do a more rigorous treatment later on, but at this point we will make it fairly simple. Okay. So, if we are tracking, what we are interested in is this value d phi, right. So, the net flux d phi would correspond to what? the difference in the two rates, right, because we are saying stimulated emission can happen, but that same emitted photon can also be absorbed, right, because that is also probable in this particular thing. So, the net flux is what you are trying to track, and that will correspond to N multiplied by Wi, and that is integrated over a length dz, okay, where what would N correspond to? Net emission, N2 minus N1, that is the N corresponds to the inversion that we have in the system. And that inversion is created by, in practical sense, that inversion could be created by an external source. We are not considering that, we are just considering the transition between these two. So, you can rearrange terms and you can say d phi over dz will correspond to N times Wi, but now Wi I will actually write out. Wi corresponds to d phi over dz, it corresponds to phi of z multiplied by sigma of mu, okay, and the solution for this will be phi of z is given by phi of 0. What is phi of 0 here? We would say that is the incoming photon flux density, right. Phi of 0 multiplied by exponential of gamma of mu multiplied by z in this case, right. So, where gamma of mu is representing n multiplied by sigma, right. So, gamma of mu is representing that inversion multiplied by the transition cross section, okay. So, if we were to look at the gain in the system, now we are saying is the total gain of the system, which corresponds to the flux density at the output of this entire length d divided by phi of 0, that will be what? Exponential of gamma of mu multiplied by d, right. So, that is the gain that we get from that medium. Gamma of mu corresponds to the inversion, right, and multiplied by the transition cross section. The transition cross section is given for a given system, you are not going to be able to change that, okay. But the inversion you can change through the pumping, which we have not considered here, but moving forward we will actually look at the traditional systems, like we can take example erbium and see how the pumping happens, how we get inversion, and through that inversion how do we get gain, okay. So, this is just a simple model, but like I said, we'll go into more details as we move on, okay. Well, thank you for your attention. We'll meet again in the next lecture.